All right, so I hope everybody's back, enjoyed the lunch and the view.
Yeah.
Not lunch yet, so break. My name is Zipplies, and I want to talk a bit about an area that has drawn a lot of attention recently, but actually it's been around for a long, long time, about what we have in the embedded market, how we're addressing this with our software development tools. So, in the beginning, the world was empty, except for just a few big machines that were fed on punch cards by those who knew, and nothing else. That was before anybody thought that these things would ever get something portable out there. And then the sun rose, and with it, a tiny little processor came up on an area that was specialized devices, which is what we now call embedded. So actually, except for those big monsters, everything that has been around when digital computing started was actually embedded devices. So it's nothing new that we're really talking about. It's just been sailing a bit under the radar after the time that when all these things, this continuum was filled with desktop, laptop, and whatnot, everything we have now. So what I want to talk about, or what I want to show you here, is that we now have this continuum of computing, but it actually, the two ends of it existed a very long time ago. It's just getting more diverse on the right-hand side now, and Intel is lucky to be able to cover all of these areas. Now, why has this become so much of a topic lately? It was not only when Intel had processors that had a really low power consumption, like with the Atom processors, that we could actually venture out into this handheld and embedded markets where performance per watt matters. You see a lot of these application areas scrolling to the right, but we have been there before, actually, with what we call the big cores. If you think about telecom equipment, if you have big racks, it's also dedicated functions, not PC-like. So this is what we typically call embedded. We have been there before, but now we're seeing a lot more adoption with the processes that we have with Atom that has been going out since its release in 2008, and seeing a lot of adoption there. And we like to fuel that. Just yesterday, we released the next version for the Atom Z670 for tablets, the Oak Trail platform, went public yesterday. So we're hoping to see a lot more adoption there and driving into the tablet and handheld markets. Now, this is just to show you why we need to address this also from the tool side. And I want to go into more characteristics on what is specific for embedded on the development tool side. And there's different scenarios. For example, if you think about a pure native development, you have your PC-like, host obviously, and you have your PC-like target. So you can easily develop on your host for the target system. It doesn't really matter that much. It has a keyboard, it has a screen, so it's pretty much the same thing, the host and target. Now, if you develop for embedded tools, you may not have a PC-like target. It may not even have a screen. It may have a very small screen. It may not have a keyboard. So you need to do cross-development. You develop on the host and download your executable to the target, and you need to handle this cross-development scenario also with the tools. So, typically, this is non-standard PC architecture. And think about smartphones. Well, tablets are kind of an intermediate thing where you could think of, why not install the tools on a tablet? May not be a good idea. After all, if the size of the screen is small, or if the power just is not good enough for handling your compilations. So cross versus native is one aspect. The other aspect is that has been before. You have system developers and application developers. Now, what's the difference? The system developers are these guys that create the hardware, that actually take the processor, build the platform, and then got to have an operating system running, for example. So they need to deal with low-level access to the hardware, do some debugging on a very low level to get the operating system up and running. And in the PC world, this was typically a rather few number of system developers of the big OEMs feeding a huge number of customers in the end that would develop their application on top of those systems. So an application developer assumes he has a working platform, a working operating system. So he can use the standard development tools there and assume, yes, a working platform, while the specific requirements typically come from the system developers. Now, what are the characteristics? I want to repeat this picture over and over and add some more information. So, as I said, typically on this left-hand side, there is more native development. Obviously, there is a blend over anywhere in here. And on the right-hand side, towards embedded, you have typically more this cross-development scenario. Another characteristic is that on the desktop laptop side, you usually have general-purpose operating systems like Windows, Linux, and on the embedded side, you have specialized operating systems. You have real-time operating systems. You have very proprietary closed operating systems that are targeted to a very specific application. So you cannot possibly use development tools off the shelf on that area. And also talking about system developers, as I mentioned, you have rather few in this general purpose computing area, but on the embedded side, you have a lot of small OEMs that develop specialized specialized hardware with maybe their own operating system. So the requirement is much more diverse for system development tools and much higher, so that you have to serve a much higher number of system developers with very different needs in that area. So in summary, we see there are different requirements and specific requirements if you want to address the embedded market. So how do we address this right now in our tools portfolio? On this left-hand side, I just want to briefly mention what we have. You heard that a number of times before. So on the HPC enterprise side, this is more the cluster tools, typical domain for cluster tools, and Parallel Studio XD. I try to make that a very cloudy thing in here because, as I mentioned, there's a lot of overlaps. But in the following, I want to focus more on the right-hand side, in the towards cross development areas, where we address, let's say, the application development side with the ABAP suite for MeeGo, so that goes more in the smartphone areas, and on the, let's say, deeply embedded side, we have this embedded software development tool suite that is targeted at that also targets system developers. So in the following, I just want to ignore the left-hand side and focus more on features on the right-hand side. So this ABAP SDK suite for MeeGo that we have right now, it's actually not a genuine Intel product in the sense like all the components are from Intel. Right now, it's part of a tools offering that comes from parts from Nokia, parts from open source, like you have the Qt Creator IDE from Nokia. You have you have a GCC compiler, this is what you can actually get from the download page right now. And there's possibilities for simulation or emulation of your target. If you develop on the host, as I said, you may not have the target available yet, so you can also use simulation. And the tools that you are familiar with are targeted at specific tuning scenarios. They are not, let's say, they are not required. We're not mandating that you need to use Intel tools, but we're suggesting that these are for optimizing applications that you want to develop for MeeGo. So we have the familiar feature amplifier XE, the compiler, IPP libraries, and threading libraries there. So you can download them and integrate them into a Qt environment and build your applications optionally either with GCC or with our compiler and the tools. So this is what we currently have. From what I'm telling you, you may hear that it's a bit of bits and pieces right now. We're working on a more integrated solution. I want to briefly go into that in the future outlook section. The embedded software development tool suite is actually also a combination. Now this is a complete Intel product containing the compiler, IPP. Now lately we replaced the old VTune that was in there with VTune amplifier XE and has an application debugger that usually also you get together with the compiler. But what is specific to this package is the JTAG debugger. So JTAG is an interface specification for low-level access to the CPU, which is used for either testing scenarios or for debugging. So you actually hook up directly to the processor and can hook up a debugger through this JTAG interface. The JTAG interface itself, it's a piece of hardware that you need to have between the host and the target. This is not part of the tool suite. You can use several, well, right now we have a third-party vendor from McGregor who offers such a JTAG probe in between. And together with that probe, you can start your debugging right away from the reset vector. So if you are into really low-level debugging, you can follow through the execution of your program from on each assembly step throughout the debugging process. Now we just added lately a couple more features. This specifically the JTAG debugger, as I said, as it is targeted onto specific processors. It has, we need to update it with every processor that comes up. It provides access to processor-specific registers. So it's a constant way of updating this product with new processor support for the JTAG debugger. And of course, as the MeeGo operating system or Linux systems evolve, we're also adding some more support there. The different platforms also have different flash paths. We have a flash writer there in the JTAG debugger. So these are current couple of new features that we're adding lately. For real-time operating systems on the, let's say, deeply embedded end, we currently have a compiler for the QNX Neutrino RTOS. This is an optional package that you can purchase from Intel to replace or to enhance the compiler that comes with the Neutrino operating system. This is what we have for this specific operating system, and for VxWorks in combination with our cooperation with Wind River lately, we provided the compiler and IPP and to Wind River, and they actually integrated it into the VxWorks 6.9 platform that was just released a couple of weeks ago. So you have the Intel compiler there as an optional compiler to develop for VxWorks. And Wind River also offers an on-chip debugging add-on or a package. This is this piece of hardware, the JTAG Pro, together with specific features that allow you to access the hardware. As I said before, we have this in our JTAG debugger, and we also provided those hardware-specific features to Wind River, so they enhance actually what Wind River offers there for their on-chip debugger. So right now, this is what we have. Of course, on the real-time operating, on the right-hand side, if you remember the picture, there's a lot more operating systems, a lot more vendors, and it's a challenge how to address all of these. Should we address all of them? Should we focus on a few? Right now, we think that going through Wind River, and I think that was mainly a driver for the acquisition of Wind River. Wind River is very well established in this market. So we have a good venue into the embedded developers market, and we're trying to work through operating system vendors to support our architecture in this area. So in the following, I want to briefly look at some of the features that we have in this product in detail. First, a couple of issues that matter most to those developers. Now, for MeeGo, obviously we're talking about developers that may have developed applications for Android already or for iOS. And so we want to make it easy for them. I mean, they're used to some very easy development environment. Eventually they want to get their application built very quickly, upload it to the App Store, and make some money with it. So the real focus here is on ease of use from setup of the build system through publishing of the application. This is what matters to these guys. Now for system developers, as I said, typically the OEMs that need to bring up the board, get everything running, get the operating system up and running. For them, debugging on the low level to leverage mostly all of the architecture features is mostly of interest, and also they will need to look at tuning drivers, for example. So they need to have good architecture support and tuning capabilities, and eventually, of course, reduce the time to market for the new device. Now, just a quick look at how this looks right now. In MeeGo, this is the Qt Creator build environment, and pulled out one picture here to show you that we can define the build steps. I mean, this is not an Intel product. I'm just showing that this is the environment that we're currently offering for MeeGo developers. And you can optionally specify here to use the Intel compiler. Once you go more into when it goes more in detail, then you can set up your target and target or projects. You can say either if you have an actual device sitting next to your host system, or if you want to use an emulator or a simulator, and then when you click test, you can verify if you have the right operating system on the target set up. Then when it goes to building, you just say build, and once it's completed the build, it will automatically download it to the specified target, no matter if it's emulator or actual device. Download it and start the remote application. So that's the very brief walk through the development steps in this build environment. So, talking about remote development or cross-development, as I said before, it's not practical, or in many cases it's not possible to install, for example, return amplifier on your target, but you want to collect data. I mean, you don't actually want to use the target as a development host, but you want to understand how your application executes on the target. So the way to go there is to set up your analysis type on the host, and then take the command line that actually collects the correct data, push it down to the target system, and execute a data collector that you installed on the target first, and then it's a command line application that runs on the target, that writes a couple of files, and when it's done, you transfer the files back up to the host, and then you analyze it in your familiar featured amplifier environment. And just there's a nice little feature. It's not really automated yet. We're working on that, on the actual kicking off of the remote data collection process. But the nice thing here is if you click on this button here, get command line, it will give you the full command line as it would start on the host, and you can copy it to your paste buffer and then just copy it down to your targets. You don't need to worry, depending on what analysis you pick out of this list or what you may have set up yourself. It may be quite a long command line here with all the options, and instead of sending it to the documentation and figuring out what options to set, you can just put this into your paste buffer, paste it into a text file, or push it down to the target and execute it there. This is a picture of the debugger GUI, how it looks like. So we have this on Linux. This is a Linux-hosted debugger. It's based on some libraries that give you the Eclipse look and feel. It's not integrated into the Eclipse IDE, but it's a standalone GUI. And it gives you all those nice little things that a system developer wants: an assembly window, a source window. You have typical evaluations. You also have specific things like address translations for translation of physical to linear address and all that. It gives a couple of handy tools to navigate around on your system. It has a trace support. I'll go into that a little in the next slide. And so, in short, this gives you all the tools at hand to handle this cross-debugging situation where you need to control the target from the host, and you get some deeper insight into the processor. And one nice feature, I'm going to show all this more in detail and live in the afternoon, but for those who will not be there, this is a bit field editor. So usually these devices get more and more integrated and have more and more peripheral chips, peripheral registers on the chip. So right now it's up to 400, 500,000 registers. Now, if you imagine a system developer that needs to make sure that all this stuff is set up correctly, it can be a very interesting challenge to navigate your way around. So what you can do here is actually you pull out, you open a register view, and then you can look at a specific register. And now, in the past, you would have probably known where this is located in memory, go into memory, and then, if this is not set up as you want, you maybe fiddle with the memory directly, which could be very difficult and very dangerous if you're not 100% sure what you're doing. So what we're offering here is a bit field editor for this register, where you can click on the individuals, you see the individual bit groups, how they are displayed here, and the whole documentation for each of those bit groups is provided in this window underneath, so you don't need to look it up in the big manuals, what each of those bits mean, and then you can actually change them on the fly. They turn to red if you modify them, and it immediately gets written to this register. So if you imagine that you had an assembly file, possibly that set up all those registers, changing one of these registers would have meant otherwise going into the source file or assembly file, flip a bit, recompile, download, and all that. And here you can just do that on the fly, touch the target, so to speak, and flip the individual bits and see what happens.